Hello and welcome to this video that discusses the property of waves. In this video we're going to look at different types of waves, the properties of waves, the speed of waves, and waves and energy. What is a wave? A wave is simply the motion of a disturbance. If we think about this wave right here in the water, let's say we drop a rock on the water surface and it falls through there and creates a wave. This disturbance of the rock falling into that water on the surface causes the points right around it to move, and those particles cause the particles near them to move, which cause the particles near them to move, and so on and so forth. And as long as there is energy, that energy is transferred and that wave continues to propagate out away from the original disturbance. A mechanical wave is a wave that propagates through a deformable elastic medium, like this water. The water is the medium. The medium is simply the material through which a disturbance travels. The wave travels through that medium. Not all waves require a medium. Some examples of those would be electromagnetic waves, such as light, radio waves, microwaves, X-rays. They can travel through a vacuum. But a mechanical wave, it requires a medium. So let's look at some different kinds of waves. A pulse wave is simply a single non-periodic disturbance. For example, one pulse produces a single non-periodic disturbance, whereas a periodic wave would be a wave whose source is some kind of a periodic motion. So let's say this person, instead of one pulse, were to continue to repeatedly move with periodic motion, that would create a periodic wave. A sine wave is a wave whose source vibrates with simple harmonic motion. So it's a type of periodic wave, but the periodic motion is simple harmonic motion. Here are some examples of sine waves. Now let's take a look at the transverse wave. In a transverse wave, the particles of the wave vibrate perpendicularly to the direction of the wave's motion. So if we have a transverse wave that is traveling like this, the motion of the wave itself, it's propagating in this direction. From here, the wave itself is traveling that way. The motion of the particles, however, are this way and this way and this way and this way, and they are perpendicular to the direction of the wave's motion. And there are a few things that we should note about a transverse wave. Transverse waves have wavelength. And remember that a wavelength is the distance the wave travels during one cycle. Another way to think about it would be the distance between two adjacent similar points of the wave. So oftentimes we call it from trough to trough, or from crest to crest. These are the troughs. The troughs are the lowest points below the equilibrium. The crests are the highest points above equilibrium. And the wavelength would be the distance between two adjacent similar. It could be between here and the next adjacent similar place on that wave as well. Let's look at a longitudinal wave. How is it different from a transverse wave? Well, remember, in our transverse wave, the motion of the wave was perpendicular to the motion of the particles. In a longitudinal wave, the direction of the wave's motion is parallel to the direction that the particles vibrate. Right here, there's a longitudinal wave. So if the wave is traveling this way, that's also the direction of the motion of the particles. They are vibrating this direction and this direction. Notice in a longitudinal wave, there are areas where there is compression, and then areas where there is stretching or expansion. We can represent that also by a sine curve, and when we do that, if we represent a compressional wave or a longitudinal wave, sometimes they're called compressional waves, if we represent it by a sine curve, then the crests correspond to these compressed regions where there's much more density, and the troughs here correspond to these stretched regions. Sometimes these are called compressional waves or pressure waves or density waves for that very reason, because the crests represent the regions of high density and pressure, and the troughs represent regions of low density and low pressure. So how can we know the speed of a wave? That means we need to review a few ideas here: frequency and period. For a wave, the frequency, which is designated lowercase f still, is the number of crests or troughs that pass a given point in a unit of time. Very similar to the definition we've given for frequency, we're just applying it to a wave. A period is the same idea that we've used as well, and when we apply it to a wave, the period with a capital T is the time it takes for a complete wavelength to pass a given point, because that's one complete cycle. So how do we use this information to find the speed of a wave? Well, we know that velocity is the change in displacement per the change in time. For a wave, the displacement of one wavelength occurs in a time interval that's equal to one period of vibration, or capital T. Remember also that frequency and period are inversely proportional, so frequency equals 1 divided by the period. We can rewrite this equation here as 1 over t times lambda, and if frequency equals 1 over t, we can substitute that into this equation, and that gives us frequency times wavelength is what is equal to the speed. So here is our fancy equation that we just derived. The speed of the wave is equal to the frequency times the wavelength. Speed is going to be in meters per second. Frequency is always in hertz, inverse seconds. Wavelength will then be in meters. We can have different differences with speed and wavelength as long as they correlate. The meters will correlate, will need to correlate, and the seconds, this will have to be seconds as long as the frequency is in hertz. The speed of a mechanical wave is going to remain constant in any given medium. So as long as it's in that medium, its speed remains constant. That means that if the frequency of a particular wave is increased, let's say a sound produced might have a different frequency, then the wavelength will be decreased because the speed will be maintained at the same speed. So this frequency and wavelength are inversely proportional, and the product of the two of them will always equal the speed of a wave in a particular medium. And that is as long as the temperature remains constant. When we start changing the temperature, different things happen. So remember that the speed of the wave will only change and can only change if it moves from one medium into another. Let's look at this example. Let's say the piano string that is tuned to middle C vibrates with a frequency of 264 hertz. Let's assume that the speed of sound in air is 343 meters per second. What is the wavelength of the sound waves produced by the string? I'm going to write down what I know. I know the speed is 343 meters per second. I know the frequency is 264 hertz. And I want to find the wavelength. My equation for speed is speed equals frequency times wavelength. I can plug the values into that equation and solve for wavelength. You can see that this is in inverse hertz, so when I divide by that, my inverse seconds are going to cancel out. I'm going to be left with a wavelength in terms of meters, and it will be actually 1.30 meters. So the last thing we're talking about will be that waves transfer energy. Remember that when we dropped the pebble into the pond water, and that water produced waves, and as long as energy was being transferred from particle to particle to particle, that wave continued to propagate. Waves transfer energy by transferring motion of matter and by actually transferring the matter itself. If you've ever sat in a little raft on top of a still pond and then a wave comes along, you'll know this because that wave, you can see it coming, it comes along, and then you sort of float up in your boat and go up and then back down, and that wave continues to move along, and you're not moving along with it, you just went up and down. So the energy is being transferred without actually transferring the matter along with it when we're talking about mechanical waves. Now, the rate at which a wave transfers energy depends on something called amplitude. And we can see a depiction here. We have a low energy wave with low amplitude and a high energy wave with high amplitude. This amplitude is the distance from equilibrium to either the crest or the trough. And for a mechanical wave, the energy transferred is going to be proportional to the square of a wave's amplitude. That means when the amplitude of a mechanical wave is doubled, let's say we go from 1 unit to 2 units, the energy it carries in a given amount of time interval will increase by a factor of 4. It will go from 2 units to 8 units. We can think of that in the reverse direction as well. If we have an amplitude of 4 units and we cut that in half down to 2 units, the energy will decrease by a factor of 4. It will go from 32 units down to 8. And remember when we talked about our mass spring system and our pendulum, we talked about something called damping. And damping is just when the amplitude of a wave gradually diminishes over time as the energy is dissipated. And damping is usually very minimal over relatively short distances. So for our purposes, we will disregard damping when we analyze wave motion. Here's some advanced ideas. How's the term damping applied in a musical context? What's its connection to the term in physics? Or what's the frequency range for human hearing, and how does that compare to the frequency for communication waves like cell phones, radios, satellites, Bluetooth, microwaves, radar, etc., or other waves of interest? If you have any other ideas, please bring them in, and I look forward to seeing you in class.